Graph neural networks, GNNs, have achieved remarkable success in various graph analytical tasks, but their effectiveness is often compromised in real-world scenarios due to distribution shifts. Unsupervised Graph Domain Adaptation, UGDA, aims to facilitate knowledge transfer from a labeled source graph to an unlabeled target graph. Current UGDA efforts primarily focus on model-centric methods, such as employing domain invariant learning strategies and designing model architectures. However, these methods have inherent limitations, and a data-centric approach that modifies the source graph has demonstrated considerable potential. In this work, the authors investigate the limitations of existing model-centric UGDA methods and propose a data-centric approach guided by two principles: alignment principle and rescaling principle. The alignment principle suggests reducing the discrepancy between the modified source graph and the target graph, while the rescaling principle states that a smaller graph modified from the source graph can achieve a generalization error comparable to that of a larger graph. Inspired by these principles, the authors propose a novel UGDA method, GraphAlign, which generates a small yet transferable graph for GNN training. GraphAlign employs a surrogate GNN model to map graphs into Euclidean representation spaces and utilizes a maximum mean discrepancy (MMD) distance as the discrepancy metric. The generated graph is expected to have a much smaller size and retain sufficient information from the source graph. The authors also introduce a novel initialization approach for the generated graph, inspired by the theoretical connection between GNN transferability and the spectral distance to the target graph. The authors' contributions include a new perspective on UGDA from a data-centric perspective, two new data-centric principles, and a novel UGDA method, GraphAlign. Extensive experiments on 4 scenarios and 12 transfer setups demonstrate the effectiveness and efficiency of GraphAlign, which beats the best baselines by an average of plus 2.16% and trains only on a smaller generated graph, with size up to 1% of the original training graph. The Contextual Stochastic Block Model, CSBM, is a generative model that integrates the Stochastic Block Model, SBM, with node features for random graph generation. CSBM generates a graph based on a prescribed edge connection probability matrix and node features determined by distinct Gaussian mixture models for each class. In the context of unsupervised graph domain adaptation, UGDA, two distinct CSBMs can be used to model the source and target graphs, facilitating the examination of the domain shift. A motivating example demonstrates the inherent limitation of current model-centric UGDA methods, which focus solely on sophisticated graph neural network (GNN) model design. Proposition 1 shows that existing UGDA model-centric methods would fail even for a simple case, while Proposition 2 highlights the potential benefits of adopting a data-centric approach in UGDA. A data-centric approach can modify the source graph to mitigate the inherent difference in data distribution between the source and target domains, resulting in a reduction in error in the target domain. The generalization bound for UGDA is derived, which lays the theoretical foundation for two principles that serve as guidelines for modifying source data. The alignment principle suggests modifying the source graph to minimize the distribution discrepancy between the modified source and target graphs, reducing the generalization error. The rescaling principle encourages reducing the source graph scale to achieve a generalization error comparable to that of a larger scale source graph. The proposed method, GraphAlign, generates a new graph to replace the source graph for training, adhering to the alignment and rescaling principles. GraphAlign aims to create a new graph that is much smaller than the original source graph, aligns well with the target graph, and retains enough information from the source graph. The optimization problem is formulated to guide the alignment of the generated graph with the target graph while incorporating sufficient information from the source graph. The Wasserstein distance is used as a natural objective in the optimization problem, but its minimization is challenging due to computational complexity. This research paper proposes a novel approach to address graph domain adaptation, a critical problem in graph neural networks, GNNs. The authors introduce GraphAlign, a method that modifies the data to align the source and target graphs, ensuring the generated graph retains sufficient information from the source graph and exhibits properties of real-world networks. The approach employs a surrogate GNN model to represent the mapping process, and the generated graph is optimized by minimizing three objective functions: alignment, mimicry, and property preservation. The alignment objective, measured using the maximum mean discrepancy (MMD) distance, aims to align the generated graph with the target graph. The mimicry objective, measured using cosine similarity, ensures the generated graph preserves essential information from the source graph. The property preservation objective, measured using feature smoothness and sparsity, ensures the generated graph exhibits properties of real-world networks. The authors provide a detailed analysis of the complexity of GraphAlign, which depends on the optimization process of the generated graph. They show that the time complexity of GraphAlign is much cheaper compared to traditional domain adaptation methods. The paper conducts extensive experiments on 6 transfer scenarios, including node classification tasks on citation networks, transportation networks, and social networks. The results demonstrate that GraphAlign outperforms various baselines, including vanilla URM, non-graph domain adaptation methods, and UGDA methods, with an average improvement of plus 2.16% over the best baseline. The authors provide a comprehensive evaluation of GraphAlign, including ablation studies, hyperparameter analysis, and runtime comparison. They also provide implementation details, including the architecture of the surrogate GNN model, the optimization process, and the hyperparameters used. The code for GraphAlign is available online. Overall, GraphAlign is a novel and effective approach to address graph domain adaptation, with potential applications in various fields. The authors present a novel approach to unsupervised graph domain adaptation, UGDA, called GraphAlign, which modifies the source graph to align with the target graph. The method is evaluated on various transfer settings across citation networks, airport networks, and social networks. The results show that GraphAlign outperforms existing UGDA methods, including vanilla empirical risk minimization, URM, and non-graph domain adaptation methods. The authors conduct ablation studies to validate the effectiveness of each component in GraphAlign, including the initialization strategy, the alignment principle, the gradient matching strategy, and the preservation of graph properties. The results demonstrate the importance of each component in enhancing the performance of GraphAlign. The authors also analyze the effects of hyperparameters, including the reduction rate, the coefficients for the alignment loss, and the gradient matching loss. The results show that GraphAlign consistently outperforms the best baseline model across different hyperparameter settings. Furthermore, the authors evaluate the transferability of GraphAlign under different levels of domain shifts, including structural shifts and feature shifts. The results show that GraphAlign performs the best under various levels of domain shifts in most cases, and is more effective under large domain shift. The authors also demonstrate the versatility of GraphAlign by combining it with different graph neural networks, GNNs, and model-centric UGDA methods. The results show that using the generated graph to train different GNNs with URM still exhibits superior performance compared to existing UGDA methods. Finally, the authors compare the runtime of GraphAlign with the most competitive baselines and show that GraphAlign is comparable to vanilla URM methods, yet delivers superior performance. This efficiency stems from the rescaled graph, which significantly reduces the time required for GNN training with URM. Overall, the authors present a novel approach to UGDA that modifies the source graph to align with the target graph, and demonstrate its effectiveness through extensive experiments and analysis. This research paper introduces a novel approach to unsupervised graph domain adaptation, UGDA, by focusing on modifying the source graph data to enhance transferability across different domains. The proposed method, GraphAlign, aligns the source and target graphs in a way that maximizes the alignment between their distributions, while also reducing the scale of the source graph to make it more adaptable. This is achieved through two key principles: alignment and rescaling. The alignment principle aims to minimize the discrepancy between the source and target graph distributions, and the rescaling principle reduces the scale of the source graph without losing essential information. The authors present a theoretical analysis of the generalization bound for UGDA, demonstrating that a smaller-scale source graph can be more effective in enhancing transferability. They also propose a data-centric approach for UGDA, which differs from traditional model-centric methods that focus on learning domain invariant representations or utilizing adversarial training techniques. The experimental results show that GraphAlign outperforms state-of-the-art model-centric UGDA methods when paired with various GNNs and model-centric UGDAs. Moreover, the proposed method is computationally efficient and requires less memory compared to its counterparts. The paper concludes that data-centric UGDA can be more effective than model-centric methods in certain scenarios, highlighting the potential of data modification in enhancing transferability. In addition to the proposed method, the paper provides a comprehensive review of existing UGDA methods, including those that minimize domain discrepancy metrics and those utilizing adversarial training. It also discusses the concept of data-centric AI, which emphasizes the importance of data modification over model design. Furthermore, the paper references various studies on graph neural networks, domain adaptation, and the importance of preserving information during graph condensation or sparsification. Here is a combined summary of pages 11 and 12. The research paper explores the concept of graph domain adaptation, citing various existing works in the field, including no-neighbor transfer learning on graphs, unsupervised domain adaptive graph convolutional networks, and handling distribution shifts on graphs from an invariance perspective. The paper introduces the concept of modifying data to address graph domain adaptation, referencing prior studies on data-centric graph learning, graph neural networks, and unsupervised adversarially robust representation learning on graphs. The authors then present the notations used in the paper, defining key terms such as source graph, target graph, generated graph, adjacency matrix, node feature matrix, and node label matrix. They also introduce the input space, representation space, and label space, as well as the feature extractor and classifier functions. The paper proceeds to describe the framework of GraphAlign, a novel algorithm designed to address graph domain adaptation. The algorithm initializes the generated graph by creating plain nodes, calculating the adjacency matrix, and assigning labels to ensure the same distribution as the source graph. The authors provide a pseudocode for the initialization process, outlining the steps for computing the spectral distance and selecting the optimal node set. The GraphAlign framework is further detailed, including the overall procedure for aligning the source and target graphs. The algorithm utilizes techniques such as Wasserstein distance, Laplacian, and diagonal degree matrix to achieve optimal graph alignment. Throughout the paper, the authors highlight the importance of addressing graph domain adaptation and the potential benefits of modifying data to achieve this goal. They demonstrate the novelty of their approach, GraphAlign, and provide a comprehensive framework for aligning graphs in different domains. The proposed GraphAlign algorithm addresses the problem of graph domain adaptation by modifying the source graph to align with the target graph. The algorithm consists of two main components: 1. Initialization of the modified graph, and 2. Training of the graph neural network (GNN) model. The initialization step is crucial, and the authors compare their proposed initialization method with several baselines, including random initialization, k-means, herding, k-center, and MMD distance. The results show that the proposed initialization method outperforms the baselines in most cases. The authors also investigate the impact of initialization on the loss convergence of the GNN model. They compare the loss curve of GraphAlign with a variant that uses random initialization and observe that the proposed initialization method significantly enhances the optimization process, resulting in improved convergence characterized by a reduced loss. Furthermore, the authors evaluate the transferability of GraphAlign across graphs with different homophily. They compare the performance of GraphAlign with several baselines, including MMD, DAN, CDAN, ADA-GCN, UDA-GCN, Mixup, EERM, SSReg, and MFR-Reg. The results show that GraphAlign outperforms the baselines in most cases, demonstrating its effectiveness in addressing graph domain adaptation. The authors also provide additional experimental results, including the performance of GraphAlign under different initialization methods and the impact of GraphAlign on the eta parameter, which affects the generalization bound for UGDA. The results show that GraphAlign effectively reduces the value of eta, highlighting its superiority in modifying data to address UGDA. The dataset statistics are provided in Table 7, which includes information on the number of nodes, edges, features, and classes for each dataset. The implementation details are also provided, including the hyperparameters used and the running environment. The estimation of MMD distance is also discussed, which is used to regularize the model parameters. Overall, the proposed GraphAlign algorithm demonstrates its effectiveness in addressing graph domain adaptation by modifying the source graph to align with the target graph. The results show that GraphAlign outperforms several baselines and is effective in reducing the eta parameter, which affects the generalization bound for UGDA. This research paper explores the concept of graph domain adaptation, focusing on the limitations of existing efforts in this field and proposing a new approach called GraphAlign. The authors begin by discussing the challenges posed by homophily, which is a common issue in graph domain adaptation tasks. They then introduce their method, GraphAlign, which modifies the source graph to align it with the target graph in terms of node degrees and edge probabilities, thereby reducing the domain shift between the source and target graphs. The authors also provide an analysis of the performance of their model under different levels of homophily, demonstrating that as the homophily ratio decreases, the performance of their model increases, indicating its effectiveness in handling more complex domain shifts. They also present a visualization of node embeddings inferred by UDA GCN and GraphAlign models, showing that the latter produces more concentrated clusters of nodes in the same class. In addition, the paper presents two propositions related to the limitations of existing UGDA methods and the benefits of using a data-centric approach to construct a new graph that aligns with the target graph. The first proposition states that even if a GNN model is trained using standard empirical risk minimization on the source graph, the classification error in the target domain will be at least 0.25. The second proposition demonstrates that when a data-centric approach is employed to construct a new graph, the classification error in the target domain can be arbitrarily small. The paper concludes with theoretical connections between the property of the newly generated graph and its implications for UGDA. It also provides a detailed proof for both propositions, utilizing concepts such as the Frobenius norm and Hoeffding's inequality to support its claims. This research paper explores the concept of graph domain adaptation, focusing on the transferability of graph neural networks, GNNs, between different graph distributions. The authors propose a data-centric approach to address the problem, demonstrating that modifying the data can lead to improved adaptation performance. The paper begins by analyzing the optimal classifier in the source domain, deriving an upper bound for the classification error in the target domain. The authors introduce Theorem 1, which provides a bound on the target error in terms of the source error, alignment term, and rescaling term. This theorem is crucial in understanding the relationship between the source and target domains. Theorem 1 is proved by introducing an inequality that links the target error to the optimal combined error, alignment term, and rescaling term. The authors then use the Cauchy-Schwarz inequality to further derive the inequality, providing a final conclusion. The paper also introduces Theorem 2, which focuses on the transferability of GNNs. This theorem states that the difference in representations between two graphs is bounded by the spectral distance between the graphs. The proof of Theorem 2 involves analyzing the GNN model, specifically a Clayer GCN with a one-hop polynomial filter. The authors derive an upper bound for the hidden representation difference between two graphs, which is used to prove Theorem 2. The results of this paper have significant implications for graph domain adaptation, highlighting the importance of data modification in improving adaptation performance. The theorems and proofs provided offer a deeper understanding of the relationships between the source and target domains, as well as the transferability of GNNs. Overall, this research contributes to the development of more effective graph domain adaptation methods. This research paper investigates the theoretical connections between Wasserstein distance and maximum mean discrepancy, MMD, distance in the context of graph domain adaptation. The authors establish a connection between the two distances, demonstrating that MMD distance can provide a bounded interval for the Wasserstein distance. Specifically, Theorem 3 states that given two graphs, the MMD distance is bounded by the Wasserstein distance, which can be further bounded by the square root of the sum of the MMD distance squared in a term dependent on the mean values of the two probability measures. The proof of Theorem 3 involves defining the MMD distance and Wasserstein distance and deriving a link between them. The MMD distance is defined as the supremum of the difference between the expected values of a function over two probability measures, while the Wasserstein distance is defined as the infimum of the expected value of the cost function over all possible couplings of the two measures. The authors then show that the MMD distance is bounded by the Wasserstein distance by assuming a specific cost function and using properties of reproducing kernel Hilbert spaces, RKHS. The connection between the two distances is established by taking the supremum over all functions and the infimum over all couplings. This result is significant as it provides a theoretical foundation for understanding the relationship between MMD distance and Wasserstein distance in the context of graph domain adaptation. Furthermore, the authors highlight the implications of this connection for developing algorithms that can efficiently estimate the Wasserstein distance using the MMD distance. The theoretical framework presented in this research paper has important implications for understanding the behavior of machine learning algorithms in the presence of distribution shifts. The authors' results provide a foundation for developing novel methods for domain adaptation that can leverage the theoretical connections between MMD distance and Wasserstein distance.